Atomic bonding in solids can also help us to understand the trends in melting points of different materials. Note that in both metallic and ceramic materials, the atoms are arranged in regular three-dimensional arrays, known as crystal structures, and are held together by one of the three types of primary bonding mentioned previously: metallic, covalent, or ionic. Metallic bonding is weaker on average than both covalent and ionic bonding, but it's also somewhat more variable in its strength depending on the specific metallic elements. As a result, the melting points of metals are on average lower than those of ceramic materials, but they also range widely, from minus 39 degrees Celsius for mercury up to roughly 3,400 degrees Celsius for tungsten. One interesting phenomenon that we'll study later in the course is that mixtures of some metals have lower melting points than either pure metal alone. Electrical solder is one application where engineers have taken advantage of this situation. A mixture of lead and tin, the composition of traditional solder, is 183 degrees Celsius, whereas you'll notice that the melting points of pure lead and pure tin are 327 degrees Celsius and 232 degrees Celsius, respectively. The melting points of crystalline materials are all very high, typically well over 1,000 degrees Celsius. For this reason, some ceramics, such as magnesium oxide and aluminum oxide, are known as refractory materials, meaning that they are well suited to high temperature applications such as furnaces and combustion chambers. Unfortunately, this makes it more challenging to form them into complex shapes, and so special processing techniques are often required in order to shape them. If ceramic materials are cooled quickly enough from the liquid to the solid state, it's possible to freeze in a disordered or amorphous atomic arrangement. This is aided by the presence of certain impurities that help to disrupt the regular ordered crystalline structure of the ceramic. Materials with such an amorphous structure are known as glasses, and a typical example is common soda-lime glass, composed mostly of silicon dioxide, the same material that makes up crystalline quartz. One important property of glasses is that they do not have a specific melting point like crystalline materials, but rather a glass transition temperature above which they change from a brittle solid to a rubbery or plastic-like material. This, of course, allows them to be formed into complex shapes or long, slender fibers, usually at temperatures well below the melting point of the crystalline form of that same material. In contrast to the crystalline structures of metals and ceramics, polymers are molecular in nature. Remember that molecules are discrete packages of nonmetal atoms that have strong intramolecular attractions in other words, covalent bonding, but much weaker intermolecular attractions, often known as secondary bonding. In fact, intermolecular attractions are so much weaker that most molecular substances, such as molecular oxygen, carbon dioxide, methane, and water, are either gases or liquids at room temperature. Polymers have extraordinarily large molecules with many thousands of atoms arranged as long chains of regular repeating units. Because of their large size, polymer molecules have enough secondary bonds between adjacent chains to make them solids at room temperature. But their melting points are still much lower than those of most metals and ceramics. Additionally, many polymers are partially crystalline and partially amorphous, or in other words, they have some regions where their molecular chains are aligned in a regular pattern, and other regions where they are randomly coiled and entangled. As a result, these polymers have both a glass transition temperature, where they change from a brittle to a plastic solid, and a higher melting point where they become a viscous liquid.